Hello folks, this is Tom from anti-proton.com, and I'm here today to show you how to take a sample like this guy right here and calculate the change in activity over time. This is very important, especially if you have little simple samples like this and you want to calculate what the activity is in any given time. It's very important if you're going to do any kind of research with them. You always need to be able to figure out what the current activity of something is. Now, I'm in my in-laws basement right this moment because I just bought a new house and my wife and I are waiting to go there right now, so I'm not really conducting research here. This is a basement, but in the new house I'll have an entire floor dedicated to being a complete laboratory, so maybe we'll get into some more stuff then, but for right now I don't. Anyway, this is a simple little video. I get emails about this, so I figured I would answer them kind of like this. So let's figure this out. First off, you have a sample. Your sample in this case is polonium 210. And the polonium 210 sample here is decaying at a rate of half the sample's quantity every 138.4 days. Well, that's what it says on the label right here. 138.4 days is how long it takes for half to go away. So I'm writing down on my piece of paper here, polonium 210, which is the nuclide, half-life, and I'm calling that T sub half to make it simple so that I can remember what it means. T sub half, that's the half-life, and it's equal to 138.4 days. This is a variable. You could call it X and Y and Z if you like, but if you start doing that, it gets kind of confusing as to what it means. That's why I called it T sub half. But you can call it, whatever you want. The original activity, you'll need to know that too. And it doesn't have to be the activity when you bought it, but it has to be the activity at some specified point. Some fixed point in time where I know the date, and I know the half-life, and I know the activity. In this case, activity, when I first bought this, was 3,700 becquerels. If you like, that's 3,700 decays per second per source. That's how many were decaying per second when this thing was new. All right, so we're going to figure out how much is left in it now. How long has gone by? Well, we're going to do a half-life in days, so we're going to calculate everything else in days too. If this were seconds, you'd want to calculate everything else in seconds or hours or whatever. Approximately 909.7 days has gone by since August 15th of 2011, which is about when this was made. It's handy to know the exact time. We're going to use this equation right here. The current activity, that's activity sub now, if you like, the current activity is equal to the original activity, that's A sub 0. Remember, A sub 0 is 3,700 becquerels. So the current activity is equal to the original activity multiplied by this. This is going to be E, which is Euler's number. A lot of people call it Euler's number because it looks like it's spelled and pronounced Euler, but it's actually Euler. So it's Euler's number raised to the negative of the natural logarithm of 2, because it's a half-life, divided by the half-life, multiplied by the amount of time that's gone by. This is actually reasonably simple math. Let me show it to you here. I took these variables and put them into this, and this is what I ended up with. Activity now is equal to the original activity. I put in 3,700 becquerels, right? This original activity, multiplied by E raised to the negative natural logarithm of 2, divided by the half-life, 138.4 days, right? There's the half-life, T sub 0, or sub half rather. And I multiplied that by 909.7, the number of days that's gone by, right? Very simple. And that will give us the answer. So, it will give us the answer in becquerels, and the reason it will give us the answer in becquerels is because these two days here will actually cancel one another out, but that becquerel will remain, so that's why it comes out that way. Now you can buy this calculator right here at the store for about $10 or so. This does everything you need to do this. Everything you need is in this calculator. A lot of people have a TI-83. These are beautiful. I absolutely think this is one of the best calculators ever made. It's been around forever. I own a bunch of them, and I've worn out a bunch of them. Highly useful, highly wonderful calculator. Or even the flagship if you like, this TI-89 titanium. The big question is not what can this do, it's what can't this do. This is like the ultimate calculator. Oh my god, I love this thing. Like, it sleeps with me in my bed. I like pet it at night. I have to come up with a name for it. But anyway, we're going to do this on the TI-83 because its screen is such that you can see it. The 89 screen is a little bit smaller so that you can fit more equations on, but that's not really very good when you're showing stuff on a camera. So let's put the sample down here, put this on top of it, and let's hit the on button to fire it up, and let's do the math. Okay, ready? Let's just put this into this, and we have the answer. So starting activity is 3,700 back rolls. See? 3700 back rolls. And we're going to multiply that with the multiplication button here. Multiply it by e raised to the negative natural logarithm of 2 and so on. So let me show you the trick to this. I find that sometimes calculators don't necessarily evaluate equations the way you'd expect that they would. So here's a way to make sure it never fails. All right? Step 1, raise e to the x. If you have an e to the x button, you can use it, like this e to the x button right here. I recommend, if at all possible, just use the regular e, hit the second button here, and then hit e. That gives you the e that you need right there. And then use the raise to the power of button. That's this little caret symbol here. Caret symbol, hit it. See, there it is. Now here's what I like to do. Parentheses, they save the world. Parenthesis, parenthesis. Oops. And I hit 2 parentheses. 2 times I hit the parentheses. There goes my cat, who must walk constantly in front of me. See the 2? And then after I put the 2, and you'll see why. This makes sure it always works. Then I hit the natural logarithm of 2. That's the natural logarithm right there, ln. See it? There's the ln. Put a 2 in it. There's the 2. Close it off with a parenthesis there. Divide. We're dividing it by 138.4. 130. Where's the back button? 38.4. All right, so natural logarithm of 2 divided by 138.4. It's in the next line now. And then I'm going to close that off. And then last but not least, I'm going to then multiply by 909.7 and then close it off. Now I'll solve this in just a second, but let me show you kind of what I did. To enter it in the calculator, what I did let's use the pen because you can see the pen better, is I typed the activity times e raised to the caret here of negative, then I did parenthesis ln 2 divided by, there goes the cat again, every 5 seconds he goes in a circle, 138.4 days, this is the half-life, 138.4, parenthesis, the time that's gone by, and then parentheses. So that's the reason I did the 2 parentheses at the very beginning. If you always do those 2 parentheses at the beginning, you don't have to worry about the calculator screwing it up. And if you use the e to the x button, which sometimes you do, that will produce an e like this, and it will usually have like a little area in here or wants you to put stuff. Inside of that, I would then start off with all your parentheses. And then what inside of that, what you do is you put a negative, then the parentheses, and so on and so forth. So now let's hit the solve button here. Oops, enter. Ah, forgot to put the negative. So hit the entry screen here. And then we'll hit the insert key. And then we'll put the negative in. Okay, there's the negative I should have put in. Now we hit enter, and we get 38.863 back rolls. That's what's left over. Current activity, e raised to the negative natural logarithm of 2 divided by the half-life divided by the time, or multiplied by the time that's gone by, 38.863. I'll put the actual key commands in the video, in the details, so you can just look them right up and use them. It works the same as it does in every other calculator that exists out there. Let me just quickly do it in this guy right here. 3700 multiplied by, where's the E button? Where is the E button? Multiply by, here it is, by E raised to the power, it's one of those type, of negative, parenthesis, ln 2 divided by the half-life of 138.4 days, parenthesis, multiplied by 909.7, and it comes out exactly the same. See? Beautiful. And of course, it should look the best when done on this, because this is the best. Let's try it here quickly and then we'll be done. 3700. And I'll show you one more quick thing when I'm done. So you have to wait till I'm done before you get to see the other cool quick thing. Alright, so negative natural logarithm of 2 divided by 138.4. Close that up, multiplied by 909.7. Close that up. Enter. Oops, I'm missing something. Missing one more of these. There we go. And when you do it on the TI-89 titanium, as you can see, the screen on it's a little darker. Let me see if I can. You can't see that very well, but it is certainly a thing to behold, I'll tell you that. There. Look at that. Much better. And the TI-89 can also do some crazy additional physics and calculus and all kinds of stuff. So beautiful. Now, you might be saying, well, if we can calculate decay over a period of time, why can't we calculate things like, why can't we just sit back and use the same math to effectively figure out like what's in our rainwater with a Geiger counter just by finding the decay curve and then matching it up to a nuclide? Well, the reason is that because nuclides don't always decay from something unstable like this into something stable. Sometimes they go through chains. For example, you have to solve this Bateman equation right here if you want to do something more complicated, like radon, for example. I actually solved this not too long ago. It was actually quite interesting what it came out to, but there you go. So this has been Tom from anti-proton.com, and before we go any further, let's just open this up quickly and see what it looks like. By the way, I've worn gloves before with this, and sometimes I haven't worn gloves, and I've tried to explain to people that I'm only wearing the gloves just to show good practice, but that it's not really needed. And I catch flack for that every single time. People say, oh, well, if you don't need gloves, then why do you have them on? And other people say, well, you know, you shouldn't have gloves on, then not use them half the time. I don't care. So you have complaints, deal with it. If you don't like it, make your own radiation videos. Anyway, so these are not something that requires gloves. The reality is these little samples are pretty harmless. Let's turn this guy upside down and see what we get. Oops. The joys of one-handed videography. Not much. Not much at all. Let me see if I can pause this and wait till it gets to max. Alright, that looks like about the max of it. 342 counts per minute. Yeah, somewhere around there. 336. Pretty low. Pretty low. Just out of curiosity, let's see what this guy has. This one's a year earlier. September 2012. Let's put this over it and see what it gets. Much better. Let me calculate the activity. I'll be right back. Alrighty, so this guy's around 2,000 counts per minute plus or minus. And it looks like I just did the math. 512.8 days is how long I've had this guy. So probably can't see it very well, but it looks like 283.677 becquerels is what you should be getting from this. So yeah, that's from the bad boy right here. Alright, so this has been Tom from anti-proton.com, and bye-bye.